Welcome to Brain Vision.
In this problem, we have a cable that is supported at two of its ends. Well, it's basically a bunch of ropes connected with rings, and we're assuming that these ropes have no weight, so they are lines between the rings. We have point A, B, C, D, and E. At point B, we have an external load, and we have the same. We have an equivalent load acting at point D, and then at point C we have a different load with a different magnitude. So if we look at this free body diagram as a whole, well, first we can write position vectors to all of our points, and I'm going to use, I'm going to use point A as my origin. So we have point to point B is 3 meters in the x direction and some unknown distance in the y. We know the exact position of point C here. We know the x position of point D, but not the y. And then we know the exact position of the support on the right end. And we're asked to find these two values given some values for these loads here. So if we take the entire structure, or the entire cable here, you can see that we have our balance of forces, gives us this, and we'll get two equations from there. One of the equations will just say Fex must be minus Fax. And then we can take moments about point A, so we get a moment from this load, a moment from this load, and a moment from this load, and a moment from this load. And we can set that equal, the sum of those equal to 0. And that will give us another equation for the moment out of plane. Now we can take a look at some segments of this cable. And in this case, I'm going to look at this segment here. Basically, take a cut there. And so that exposes this force, FBC. Now FBC has a magnitude of FBC and is in the direction from the unit vector from B to C. Now we can figure this out because we can figure out what the vector from B to C is, and then we can normalize it. And we can figure that out by knowing the vector from A to B and A to C. So this is, well, not known, but it is a function of our unknown variable here. So this sum of these forces has to be 0, and then I'm going to take moments about point C here. So there's no moment created by FBC because it acts through point C. There's a moment, but there is a moment created by this force, which actually is the opposite of, is the negative of this force here. And so we have the moment created by that force, and then the vector from C to A, which is just minus the vector from A to C. This will give us another 3 equations. One of them is redundant, but we can then extract the information for at least the first part of the problem, and that is that we get YB, this distance from this distance here, is 2.22 meters. We can also figure out what the horizontal load at each of these supports is, and that is 1,130 newtons, and then the interior load in the cable in the rope from B to C is 1,180 newtons. So to find YD, we can take another section, and now we're going to take a cut here and just look at this free body diagram. That free body diagram, we have P2, FE, and FCD acting. FCD has a magnitude and is in the direction from C to D, and we can figure that out in terms of our position vectors. And then I'm going to take moments about point C again. So now at this point we have no moment from FCD. We have a moment from this and a moment from this load. So those are these two here, and we set the sum of those to 0, and we'll get some more equations. And with those equations, we can figure out that YD is 1.55 meters, so that is this distance here. We can also figure out that FCD is, well, it has a magnitude of 1,220 newtons. So it is in this direction. So again, it's in tension, just the way we drew it. I actually should have used F DC here, and that would have shown that it was positive. But anyway, that gives us the answer that we're looking for. I could have also said FCD is just minus, FCD equals minus FDC. I should have put a minus sign in there. And in fact, let me do that. Let me just correct. It should have been a minus sign. And this should have been, well, we can leave it that as it is. Because the unit vector from D to C is just the opposite. That's the negative of the unit vector from C to D. Okay, so we got that. Now we can, in problem 95, which looks at the same system, we're basically just given different knowns and different unknowns. And in this case, we want the magnitude of this load if YB, this value here, is 3 meters. So in this case, we want the magnitude of this load, and then also again this sag here. So that we get basically just go through the exact same analysis, but now we have a different unknown and a different knowns. So now if we plug in YB is 3 meters, we'll find that P1 is 720 newtons in the negative Y direction, and then also that YD is 2.33 meters now. So instead, we can see that it's sagged quite a bit more. Now the loads in the, and again I should put, I should fix the sign here. This should be plus. The loads in the interior cables are now 747 newtons in the cable from C to D, and 730 newtons in the cable from B to C.